So we mixed the states in equal superposition. So what you can do is you can go back to the code and you use the same code. Please make a copy, but mix them in unequal superposition. So previously what we did was both states, I wrote that as 1 over square root 2, phi 1 plus 1 over square root 2, phi 2. But now I can do this as square root 3 by 4, square root 1 by 4. All that you have to ensure is if this is C1 and if this is C2, we have to ensure that C1 square plus C2 square, they sum up to 1, right? So we basically are doing unequal superpositions here. So use the code to look at how the expectation value will change. Think about how the nodes will look like, whether the nodes will look symmetric like the previous case or will they look asymmetric, and qualitatively try to change coefficients and the states. Instead of phi 1 and phi 2, you can mix phi 2, phi 3 or phi 1, phi 4 and mix them in unequal superpositions and try to see how the frequency is changing, right? Again, you don't have to submit this for grading, but this is for your own understanding. As Dr. Garge mentioned at the beginning of the lecture today, that for a better understanding, when you do this code, if you are able to follow math, but you're not able to visualize properly, our hope is that you can use this code to visualize things more properly, right? And check them out for yourself. So you can conceptually think what is going to happen. So what I would recommend is before you use the code, write down what you conceptually expect from whatever we have discussed. And after you have written it down, run the actual code and then see if it actually makes sense with your expectation. If it is the same, then that's great. That means you have understood it. If it is not the same, that means you're missing something. And so check whether you are wrong or the code is wrong. It need not be that you are wrong. It could be that code is wrong, right? So please check and try to understand. And if you have any questions after doing the homework problem, bring them to us tomorrow or later on as we go along the course. There is a question about should we know how to code? So, knowing Python is a prerequisite, but we are not expecting you to write the code yourself. So that's why we are providing already written code. And if you do not understand a part of the code, please use in Google Colab. The advantage is there is Gemini AI on Google Colab. So if you don't understand a part of the code, you can highlight that part of the code and ask Gemini what that part of the code is doing. For example, if I go back to my Google Colab here, let's see. So let's say I don't understand this part of the code, right? So I can where is the Gemini AI? So
it's at the bottom, middle bottom.
Yeah. Okay, I see it now. Continue. Thank you, whoever that was. Okay, so then I can kind of ask what is this doing, right? Explain this to me. There was a better way of doing this that usually it shows up right here. Explain this part of the code, but it is yeah, okay, explain what this part of the code is doing. Okay, with AI, I don't know if it spits out some answer that looks funny. So, but let's see. It should tell you that, it is making a superposition. But if you do not know how to code, you could use this kind of Gemini AI to code or to explain the code. So, but yeah, so it is calculating the superposition state in 1D infinite square well at given position x and t. Right here is a breakdown, right? So it is explaining everything to you. So you should be able to see it that way. So if you don't understand, so please make use of that if you do not know how to code. But if you know how to code, you should be able to follow. This is a pretty okay, there's a question that would making ChatGPT or Gemini or Perplexity make us dumb. If we don't use that, we stay dumb, right? If we do not know. So if we use it, it depends upon how we use it, right? If we use it without applying our own common sense, yes, it would definitely make us dumb. But if we use it with our common sense as a tool, right, as an assistant rather than as a teacher, then it should not. So use it wisely, right? Then if you use it wisely, I don't think it makes you dumb, in my opinion, at least. So let's get back to the lecture. So we have one more thing that I want to discuss, that is the another type of so there is homework problem 2. Again, this PowerPoint that we are going to email it to you. So you will have the links to the code, you will have the homework problems, and you can go through this. So here again, I did 5.1 and 5.3. So you can simulate with that code that we have, right? And then the other part of the code is to compute the uncertainty in time. So uncertainty is defined as this delta x square and delta p square. So there is even this is written in the Google Colab book. If you scroll down and check, you should be able to see it. And so you should be able to verify this uncertainty relationship. But we're going to talk about this uncertainty relationship more in the upcoming lectures. But please go through the code and see what you can do. If you do not understand this code or any part of this, bring questions tomorrow to us, and then we can discuss those. And so the next potential that we are going to discuss is called the simple harmonic oscillator. So SHO is simple harmonic oscillator. The main motivation behind this is that if I have any potential, like for example, if I take a crystal lattice, right, where the atoms are arranged in a particular configuration, right, I know the potential at a particular location, but I want to know how the potential is changing around that location. Then I can expand it in what we call as a Taylor series. In this Taylor series, you get this term. The first term is at the equilibrium, which we can set to 0. And this is the first non-zero term that matters. And this looks like half kx squared, which is which looks like Hooke's law, spring, right? Potential for Hooke's law. So that's why we call it a harmonic oscillator. That is, imagine a mass attached to a spring of spring constant k, and if you just push it, it's going to keep oscillating, right? So this simple harmonic oscillator is like a interatomic potential in a chemical bond in a very crude way, right? Usually you may have to include other types of potentials or higher order terms, but in this model, it's a simpler potential, which is time independent and non-zero, because in the 1D potential well, what we have seen is the potential well is between 0 to L, but within the 0 to L well, the potential is 0. Here it is not 0, it is changing with time. So, changing with position. So if I were to plot V of x versus x, it would look like a parabola, right? So it is not 0, right? And it doesn't go to infinity. It only goes to infinity at x is equal to negative or positive infinity, right? So then we would expect that the wave function is not 0 anywhere, right? So it spreads out, right? So we can again solve this using the Schrodinger wave equation, right? So we express the Hamiltonian, right? Recall that Hamiltonian operator we said is like minus h cross square by 2m d square psi by dx square. This is what we are writing as p square by 2m. We will discuss this also a little more in later lectures. And this is the harmonic oscillator potential. So this omega m omega square serves as k, the spring constant, like the spring constant. So previously in 1D well, when we solved with the boundary conditions and what we had, right, in 1D well, we got the solutions as phi n of x is equal to square root of 2l sine n pi x by l. We are not going to solve the simple harmonic oscillator in great detail, but if you do not understand this, you can refer to any standard quantum textbook. The simplest one you can find is one by David Griffiths. And you can look up that book, or you can just look up on Wikipedia, or you can even ask ChatGPT. Again, use it wisely, use it carefully, and then you should be able to see how these solutions come up. the most important thing is that we see here is even in the ground state, even in n is equal to 0 state, energy is not 0. So even when n is equal to 0, we get E0 is some non-zero value, half h bar omega, which we call as 0 point energy. All right. So even n is equal to 0, it is not 0. And the wave functions look like what we call as Hermite Gaussian functions. This is the Gaussian part, and this is the Hermite part. So as you can see, to understand this Hermite Gaussian, the internal structure of this, you need a lot of math background. But really, we don't have to worry about this internal structure. So we are going to use the Dirac notation, which we will see in linear algebra tomorrow. Then we don't have to worry about all these mathematical, intricacies. We can just simply denote a state as 0 state or 1 state in a ket notation, and that makes things much more easier. And so we're introducing the simple harmonic oscillator here today, but tomorrow or later on in the course, we will see how to use the Dirac notation where you don't have to remember how these states look like. But the way you solve is very similar to how we solve the 1D Schrodinger equation for simple harmonic oscillator. And so, let us go back to the simple harmonic oscillator code, and we can do this thing that we can mix simple harmonic oscillator code as in the case of 1D oscillator. And we will see that there also you can mix the states. For pure states, you would get time independence. And if you start with an initial state that is a superposition, then you get time dependence. And you can see this. And so when you get this time dependence, you will see that this time dependence, when you have a mixed state, superposition state, you can think about just a mass attached to a spring. So imagine like you have some reason. So imagine you have a spring and a mass attached to it, and spring has some constant k, and this is some mass m, right? If you look at the position of this mass as it is oscillating, how would this position be, right? You can easily see that should be like some cosine omega t, right? If it is starting from, let us say, some distance from a distance a from the origin, right? Then as you oscillate, right, it's going to be like a cosine omega t, right? So it's going to be at a distance a at time t is equal to 0, and as time goes by, it is going to go back and forth, right? So this, you can compare this to the classical motion. So whatever it is, whatever theory we are developing in terms of the quantum framework, we have explained discreteness, we have explained diffraction, we have explained coherence by building this wave function, by coming up with these postulates. Ultimately, it should correspond to the classical macroscopic observables. So that is why this question is asking you to compare it with classical motion. Because ultimately, there should be correspondence. It is not that there is a sudden breakout that, okay, until here, until Wednesday, we consider it to be quantum, and after Wednesday, it is classical, right? So there is no such sudden abrupt change, right? Whatever it is, ultimately, when you take averages over long times or long scales, it should correspond to whatever we see in classical mechanics. So again, you can go back to the code, and if you scroll down in the Google Colab, you should be able to see where this thing is coming from. So unfortunately, I think we are out of time for today. So we won't be able to cover the de Broglie today. So we may be covering de Broglie in the first part of the lecture tomorrow. But to summarize what we have discussed today is that we talked about quantum mechanics as a statistical theory and not as deterministic trajectories. We always have an ensemble here. So we are only looking at the statistical outcome, and the state is talking about how the particle is being prepared. It is about the preparation, not a property of the system. And the psi is a mathematical tool. It is not a physical property of the system. And we can define operators. For example, we defined this operator called the Hamiltonian operator, right? We said that this is like minus h cross square by 2m. del square plus V, right? And these correspond to observables. For example, the expectation value of this, the average of this would correspond to energy. The average of momentum operator would correspond to the momentum. The average of position operator would correspond to the average position. So when we talk about like expectation value of X or expectation value of P, we're talking about expectation value of these operators. And those are the actual observables that we can measure. And because it is a statistical theory, we are again going to get probabilities. And we looked at pure states, we looked at time-dependent, time-independent Schrodinger wave equations. We looked at pure states, we looked at superposition states, and we were able to look at interference. We were able to see how they mix and how the nodes come up, how they change, how they're time-independent in pure case, and how they become time-dependent when you have a superposition state. And we analyzed 1D well and simple harmonic oscillator, for which we have also seen the codes. So in the next lecture, I was going to cover the de Broglie relation also in this lecture, which we could not cover due to time limitation. So we will cover that tomorrow. And so we will cover that tomorrow, and um, uh, we will use the Dirac notation. We will also introduce Dirac notation tomorrow. So we will stop here. And Professor Gargi pointed out in the chat that please make a copy of the Google code for yourself and do not change the code directly in that link. And that if the tiny URL code is not working, then you may want to use the so some places this tiny URL code may not work. So you can use the Google Colab link directly, which is in one of the slides. Somewhere when I talk about the superposition. Sorry, 16. Yeah, so it is on slide number 16. So you don't use the tiny URL link and use the slide number 16. This is the Colab code, and you can go here and then do the homework problems. And Professor Gargi is going to send you the PowerPoint here. She already sent it, and so you should have received it. So we will stop this lecture here, and I'm going to we're going to hang around for a few more minutes if you have any questions. If you don't have any questions, what I would request is I'm going to launch the poll again. And so please answer the poll. It shows the same questions as before, but it's again at a different point of time, right? So this is a mixed state. So the expectation values of the poll are time dependent, right? So please answer the poll again. And then we after you answer the poll and submit it, you're welcome to leave if you do not have any questions. You should be able to see the poll now again on your screen. Okay, if you do not have any questions after filling the poll, please feel free to leave. If you are unable to submit the poll questions, maybe you haven't answered. If you have, maybe you did not answer one of the questions, so please check and see. There's another question again on how do I use ChatGPT and Gemini AI wisely. So the way to use that is use it as a tool. That is, look through the code first by yourself or whatever you do not understand, and try to see if you can make sense of what we make sense of the code based on what we discussed. And write down, maybe list whatever you understood. And then to check, you can like how I showed you, you can cut, copy, paste into the box and see what it is saying and see if that is fitting with your understanding. And once you understand that, you can check with us to see if your understanding is correct or not as we go through the course. But you don't have to blindly believe what ChatGPT is saying, right? So as you do the homework questions from 1 to 4, like for example, let's say you use ChatGPT for understanding the code for the first question. Then for the second question, do not use ChatGPT. Try to answer it by yourself based on the knowledge you gain. And then, you should be able to get the right answer if you understood it properly, right? Rather than simply blindly pasting it into GPT and asking it to answer. So that's how I would say you would use it wisely. Oh, we have a question. Saptagiri, please go ahead and unmute yourself. And
Yes, sir. Sir, I have one question. we have these probabilistic amplitudes changing over time when
Yes.
multiple particles are interfering, right, as an ensemble, right? So they are evolving over time. So will that evaluation will always be constant? Suppose say if I conduct multiple experiments at time t3, will I get the same amplitude always over multiple experiments? I mean to say, when I say experiments, observations, for multiple observations.
Okay, so I guess what you're asking is, let us say we have a particle in a infinite square well. If I make 3 such square wells which are independent from each other, and I take a picture of this infinite square well at 1 hour on all the 3 wells independently, will I get the same result in 3 wells? Did I understand it correctly? Is that what you're asking?
No, when all those three are in superposition, 3 states.
Yes, 3
When
states are in superposition in one well, right?
okay, yes, sir, yes,
Right.
yes,
So I'm
yes,
preparing this superposition state. Let us say I prepare 5 copies of this superposition state. 3 states in superposition, 5 copies,
yes, sir,
right?
yes, sir.
And what you're asking is, I make a measurement on this. Will I get the same result on all the 5 copies? Is that what you're asking?
Yes. That
Yeah.
is,
Yeah.
yeah.
If you do like that, yes, you should get the same result. The statistical average should be the same result. Yes.
And
That's
at different time intervals as well.
I mean, so if you measure all the 5 copies so let's say the first copy I made, I measure it at t is equal to 1 hour. The second copy also I measure at t is equal to 1 hour, right? I should get the same value, right? If the superposition states are the same, right? But if I measure this at time t is equal to half an hour and this time t is equal to 1 hour, then the result will be different.
Okay. I get this first part, sir.
Uh-huh.
Let us take the single copy, right? On the single copy itself, I'm making multiple observations at 2 different time intervals, because we saw that in the video that you have shown. Over
Right.
time, it is
Okay.
oscillating. Amplitudes are oscillating.
Correct.
So at
So
T3, the
mhm.
amplitude may be 3. At T5, amplitude may be 0.
Yes. So that
So
will be oscillating. Yes.
oscillating.
Yes.
So
But
first
also,
observation, yeah.
sorry, go ahead. But also, one thing that we are going to look at is, once you have made the observation, what happens is ultimately your device is going to become part of the system. So, to suppose I have to take a picture or I have to measure for measurement, I need to somehow interact with the system. Without interacting with the particle, I cannot measure it.
Yes.
Right. So because I cannot measure it without interaction, then I am going to ultimately end up changing the state of the particle, because the preparation state has changed. Because now in the preparation state, now the device is also included. When I first prepare the state, there is no device. There is no camera that is taking pictures. Right. Now, once I have taken the first picture, the camera has also become part of the system. Are you able to see what I'm saying?
Okay. It's like we took the measurement already. So
Yes,
even
we
if I
took the.
measure again, I will get the same value again.
No, you won't get the same value again. You would get value based on how you measured it. So
Yeah.
it would, the measurement itself would change. The measurement is a different state of preparation. So now, in the first case, your preparation is your particle is in a well. That's it. That is your preparation procedure. And
Yes,
your
sir. Yeah.
measurement is taking a picture. That is the first step. For the second measurement, your state preparation is, you prepared the particle, took one picture, and then you are taking the second picture. So the preparation procedure is different. That is, you have prepared the particle and took one picture. That becomes the preparation procedure. Are you able to see what I'm saying?
Yes, sir. I could see that now. Yeah, thank you.
Yeah. So the preparation
Yeah.
procedure itself has changed, so the result will be different.
Yeah. Thank you,
Yeah.
sir.
Okay. No problem. And also, all of you, please feel free to address me as Ram. And I feel a bit uncomfortable people calling me sir. So please feel free to address me as sir. Sorry, as Ram, not as sir. Thank you. Any other questions? Oh, okay. There is one question in the chat. Is the wave mechanics part really necessary for a novice who wants to learn quantum mechanics? I mean, wave mechanics, in the sense, if you're talking about wave mechanics of classical waves, or I mean, in general, usually we call quantum mechanics itself as wave mechanics. So, or can, oh, okay, you're saying Dirac notation and vector algebra. No, I mean, it's usually introduced with wave mechanics, right? And then you go to Dirac notation. So I introduced with wave mechanics because some people may not have the background in linear algebra. So tomorrow we will be going to vector algebra. And so if you are familiar with Dirac notation, you can directly start from Dirac notation. So usually when I or even Professor Gargi, we usually are directly dealing with Dirac notation most of the time. I think at least I rarely use quantum mechanics unless I'm teaching a course. So mostly we are doing only with Dirac notation and linear algebra because it makes things much easier than the wave mechanics, whether it is notation or anything else. So my suggestion is, if you are familiar with Dirac notation and vector algebra, please go ahead and you can start from there. Okay, I think everybody answered, so I'm going to end the poll. I'll wait around to see if there are any other questions. Are there any other questions? Going once, going twice. So are you able to see the results? Right. So this is just a revision of what we did yesterday. So most of you answered the first question correctly, that the statistical description of an ensemble of identically prepared systems. So whoever answered it as the charge density of an electron cloud, that's not really true, right? Because wave function does not need to represent only electrons. It is in general, right? And it is a statistical description and not the charge density, right? You can even have, for a neutral particles also, you can have a wave function, for example, right? Then let's see the second question. Again, most of you answered it correctly. Someone said a single detection. A single detection doesn't give you a probability at all, right? So for probability, you need multiple measurements, right? So please check that, whoever that is. And then the superposition states, that's also most of you answered correctly, that stationary states have constant probability densities, the expectation values are constant, while when you have a superpositions, you could have time-dependent patterns. And then this is the question that I think most of you did not answer correctly. So when you prepare, recall that wave function or the state is the preparation procedure. So if I make a measurement, then for the second measurement, the preparation is whatever was the initial preparation plus the first measurement. So when you make the second measurement, the way you prepared the system has changed, because in the first measurement, you were doing the first measurement right after the state was prepared. But for the second measurement, it is right after the state is prepared and the first measurement. So the answer should be B. That is, the preparation has changed for the second measurement. So there is a question here: if the coherence length of the source is less than the phase difference, would there be any interference even in the coherence length? So I am not sure what you mean, Priyanshu, what you mean by coherence length. Because I think you are talking about like laser coherence length, where you have a beam of light. I'm not sure what would be the coherence length. So, sort of. So when we do the electron interference experiment, it is not. So when we do the interference experiment with light, you have a beam of light, two beams of light that are interfering. So you have all these multiple photons at the same time. But in case of the electron double slit experiment that we have seen yesterday, it is not like that. We don't have a beam of particles. We have identically prepared electrons emitted one by one that we were detecting as single unit. So the wave structure appears only after you have collected multiple particles. So I'm not sure if we can define a coherence length in that sense for a beam of electrons. So I hope that answers your question. And going back to the quiz here, so please check fourth question. Why the second option is the right answer, and then we will proceed to discuss the de Broglie relation, which we left out yesterday, and following that. We will do Dr. Gargi Sharma will talk about the Dirac notation. And after that, we will do in the second part of the lecture NumPy, and maybe if we get time, some introduction to Qiskit, where we can sort of get to some qubits. So let me share the screen and okay, I hope you're able to see the screen. So this is a summary of what we did yesterday, right? That the quantum mechanics is a statistical theory. It is not deterministic trajectories, but even if you want to think about it as a trajectory, you can think about it as like trajectory of ensemble if you force me to say that. But I would say that it is not for a single particle deterministic trajectory, but we rather treat the state of the quantum state of the particle that encodes the preparation. And anything that is physically measurable, for example, position, momentum, energy, these we express them in terms of observables or operators. So for example, as you can see on the notepad, yesterday we defined the Hamiltonian operator, right? So for example, we said that this minus h cross square by 2m del square plus v of r is Hamiltonian operator. So if you did operated on the psi, then in the time independent Schrodinger equation, we would get, energy, which is the observable. Again, when we measure, we only measure the average, the ensemble average. And this ensemble, again, is not a multi-particle ensemble. It is single particles identically prepared, right? And to get the probabilities, we need, psi square, that is psi star psi, right? And then we looked at superposition and interference. We analyzed 1D well and SHO, right? And we had some homework problems. I hope you guys had a chance to go back and look at the homework problems and work with the code. If you have not done that, please do that. Even if you are familiar with quantum mechanics, I highly encourage you to do that so that you get warmed up. And it is very hard to come out of this state as a physical property of the particle itself. So please bear in mind that the state is not a physical property here. It's a mathematical tool, mathematical concept. So that said, now let's look at what is the meaning of an ensemble, right? So when we have, let us say, in the Hitachi experiment, we have, let's say, a tungsten source, right? That is emitting electrons, right? That's emitting electrons. And so these electrons are coming one by one. And here we have sort of a biprism, right? And then here we have a screen that is the detector. And so, somebody was requesting to record. Sorry, I have to decline that because I'm already recording it here. And we were told that can we allow personal recordings? So unfortunately, we are not supposed to allow the personal recordings according to the GAN course. So, but my understanding is that after all the lectures are done, these will be sort of posted somewhere so that you will have access to them. I'm sorry, Shivam Garg, that I had to decline your request for recording. My apologies. Going back to the Hitachi experiment, so we have a tungsten source that is emitting electrons, and we have two slits, and we have a detector. And if you remember, then we were seeing these as localized hits, one here, one there, at some place, right? So to discuss these, to describe these events that we see, which eventually become like fringe patterns, right? So we have seen this yesterday, that over the time, they become like fringe patterns. But initially, they look like dots on the screen. So whatever theory we develop, like we discussed yesterday, we need to include both the localized hits as well as the ensemble patterns that emerge. So we started with saying that, we could express the wave structure that is associated with the particle, right? As beginning with a plane wave, right? So e to the power ikx, that is a plane wave that is spread out from minus infinity to plus infinity, right? With a single momentum. So it's just going to be spread out everywhere. But for looking at these localized particles, we started building wave packets. So what we did was we took a bunch of momenta, right? The e to the power ikx that you see here in the second bullet point. So we took that 5k of, so we took, we wrote psi of x as 1 over square root 2 pi, which is, and phi of k e to the power ikx dk, right? So this phi of k is the weight. Right? So it's the weight that we are giving to different momenta, and we're collecting a bunch of momenta, right? So if you have a single momenta, single k, right, then the particle is going from minus infinity to plus infinity, completely delocalized, right? And so if we have a few momenta, a few k, then we can localize the particle, right? Let's say medium localization, right? And if we include more k, then I can completely localize it like the dot on the screen, right? So that's how we were able to build a wave packet that could explain the single detections, right? And then we talked about the interference pattern, how this interference pattern emerges from that. So the de Broglie relation, basically what it says is that this momentum P of, when we talk about this P, this whatever observables that we talk about in quantum mechanics are statistical outcomes. There is no single particle measurement. You have to keep that in mind, because when we talk about this momentum P being related to h bar k, right? Here, when we say h bar k, it is not describing for a single particle. It is rather describing the wavelength or the wave number that is associated with an ensemble of similarly prepared systems. If you do not understand this correctly, then it can lead you to basic confusions and make you think that quantum mechanics is different from your common sense. There is a question in the chat. Let's see. There's a doubt. Motion of a single particle identically prepared or motion of single particle multiple times. Both are ensemble. So when you measure single particle, that's a single measurement. But for example, like when we look at this here on the screen, when we look at the Hitachi experiment, I have one electron coming out. That one electron comes out and falls somewhere on the detector. Then another electron, right? Let's say this is the first electron. It came out and it is spotted here. Then another electron, second electron comes out, which is identically coming out of that tungsten. And then maybe the second electron falls here. So it is the same type of particle that is coming out of the same preparation system, but we are measuring that multiple times. I hope that answers your question, Anuradha. So that's what we mean by ensemble of similarly prepared systems. And so this wavelength that is associated is not with respect to just a single particle. It is rather a wavelength that is associated with similarly prepared system, and it is belonging to an ensemble. So it is not that the particle is behaving both like a particle and a wave. That is just completely against common sense and wrong to think about that single particle as a wave. Here, when we talk about de Broglie relationship and wave-particle duality, what we mean is when I have individual electrons, I still get these localized hits like we saw in the Hitachi experiment. But when I collect multiple of those, when I make an ensemble measurement, that's when I see the pattern. So the wave structure is associated with the state, that is the preparation procedure. It is not that this is a wave that is attached to a single particle. You see? So the wave nature is associated, the wave structure is associated with the ensemble measurement. We don't see the interference pattern in case of Hitachi double slit, like until we have collected multiple particles, right? So that's the main thing here. The de Broglie relationship is relating to a wave vector or wavelength or energy, E is equal to h bar omega. These are averages that are coming out of the ensemble measurement. These are not, it is not that a single particle has a single wavelength, right? And so if I look at the wave packet, right? So you cannot make a wave packet for a localized particle with just one momentum, right? Because we have seen that if I have just e to the power ikx, like we have seen here, e to the power ikx, that would be spread out from minus infinity to plus infinity, right? So because e to the power ikx is simply cosine kx plus I sine kx, and they never die down, right? So they oscillate between 0 and 1. So no matter what x is, from minus infinity to plus infinity, you would have oscillation between 0 and 1, or minus 1 and plus 1, right? So I cannot represent a single particle with a single momentum, right? I need to combine a lot of different momenta to make the wave packet. And so here we're combining these different momenta, and the average of those is what we are relating to the K here, the K average, the expectation value of all the momenta that I have included here. So here in the expression of psi of x, right, we have phi of K, which is the weight, times e to the power ikx. So I can get an average K, and that is what we are relating to the momentum in the de Broglie relationship. So we cannot really represent a single particle with a single wavelength. This is the average, ensemble average. And that's to be borne in mind. So what the de Broglie doesn't mean is that the material wave is not glued to a single particle. The wave nature is related to the state. So the state is not a property of a single particle, and it is talking about the preparation procedure. So the single wavelength or the single momentum that we're talking about in de Broglie is not a single wave glued to the particle, but rather coming from the ensemble. Single runs still give you single localized outcomes. Wave features only come in statistics across the ensemble. So this is the part that we could not cover yesterday in regard to de Broglie. So I hope this gives you a better idea of wave particle duality. Often wave particle duality is discussed in a very confusing way, as if the particle is both wave and particle at the same time and in the same way. This is against the first principle of logic, right? All our logic is based on the principle of non-contradiction. That is, I could say it is either raining or not raining. It cannot be both be raining and not raining at the same time and in the same way, right? So we have either X or not X. We cannot have both X and not X at the same time and in the same way. So that is against our common sense. So here, when we talk about wave particle duality, right, we are not breaking that principle of non-contradiction or principle of identity. We are rather, what we are saying is that the state preparation procedure, we cannot measure exactly, and we only can measure statistical outcomes. And whatever wavelength we are attaching to that, that is coming from the average wavelength, that many case that we use to build the wave packet that you see here. So it is coming from many of these wave structures, many momenta that we are using to build the wave packet. Right? I hope that point is made clear. So I'm going to stop here, and then Dr. Gargi Sharma is going to talk about the linear algebra part and direct notation. But before we do that, I would like to stop and ask if there are any questions. Okay, so there are some questions in the chat. Okay, so when a measurement is performed on a system, the wave function collapses. The wave function doesn't collapse. That collapse is a thing that is sort of useful for shutting up and calculating. That like David Mermin called it shut up and calculate. That is, you don't want to think about, the math is always going to work out, right? You just shut up and calculate, math will work out. But the wave function is not a physical thing. And the collapse is also not a physical thing, because the collapse is said to be instantaneous, and there is nothing that is instantaneous. So this is a symptom of being stuck in the Copenhagen interpretation. Whatever it is not a single measurement. All outcomes of quantum measurements are probabilistic and statistical outcomes. So after some time, when the wave function evolves into a superposition of states, this is clearly the problem is with the Copenhagen interpretation. So when in Copenhagen interpretation, when you talk about wave function collapse, it's not something very physical, right? The wave function is first not a physical thing. And the second thing is collapse is even more unphysical. Nothing can collapse instantaneously. Because any measurement that I need to do as an experimentalist, it requires, femtoseconds or attoseconds or whatever. It requires some time, right? So, and then when you say after some time, the wave function may evolve into a superposition, what that means is when you made a measurement, the state preparation procedure has changed, right? And so because the preparation procedure has changed, now you get a different outcome, not because the wave function has, you can talk about it like wave function has collapsed and it is evolving into a different superposition, but the truth is that it is the state preparation procedure has changed. I hope that answers that for you, Subhanshu. And then next we have Anuradha. Sir, what does that mean? Again, you can please call me Ram. What does that mean that when we observe an electron, it behaves like a particle? When we aren't, it behaves like a wave? Well, I don't know how to answer that question, because when we aren't observing, if you say it behaves like a wave, how do you know that? Like if you are not observing it, that it is behaving like a wave, right? If you say it is behaving like a wave, then you must be observing it, right? So that's the problem with the question itself. So what I would say is single localized hits, like we have seen in the Hitachi double experiment, right? So when I have one single electron being emitted from the source, that looks like a localized particle. But when I collect multiple repetitions of the same exact preparation procedure, when I collect multiple shots, then I see a wave structure, right? So it is not that the electron is behaving one way when we look at it, and it is behaving another way when we don't look at it. There's a very famous question by Einstein, that is, does the moon not exist when we don't look at it? All right, and so it is not like that. So but I can't look behind, so I don't know what is happening behind me. Yeah, you don't know what is happening behind you, but whatever is happening behind you is still happening. All right, so I can't see my back of my head, doesn't mean back of my head doesn't exist. All right. Do you see that, Anuradha? I can't see the back of my head ever, but that doesn't mean the back of my head doesn't exist, right? So, okay, there is another question from Viroy. Does single individual particle undergo superposition? So again, when we talk about superposition, we're talking about a state. The state is not a physical property of a single particle. It is talking about, it is encoding information about the preparation procedure. So when we talk about superposition, it talks about the preparation procedure, not about the single particle. So when we say it is in superposition, that means my state preparation procedure could yield either 0 state or 1 state, right? That's what it means. And if I measure multiple outcomes, then if I find, like, let's say out of let's say we will see this Stern-Gerlach experiment later, but if I measure them, half the time I would find the particle is in one state, and half the time we have a particle in another state, then we would say that is a superposition. Again, no single measurements. Get that out of your mind completely. No single measurements in quantum mechanics. The single shot measurements are what we call as projective measurement that only tell you about part of the story. But if you want to look at the state, that is the preparation procedure, you have to repeat the procedure multiple times, right? Okay. Any other questions?